because it's physical science time, babies. Okay, and today we are talking about, as you probably are already aware, magnets. Magnets. The objective that we're going to talk about is explore structure and function in magnetic fields. So please write that down also, as I do too. Explore structure and function. Oops. Explore structure. What's the word structure mean? What's the word structure mean? Let me give you a sentence frame. Like how something is structured. Okay, how something is
the way it is.
The way it is, yeah. I mean, that's not bad. That's not far off the truth. The structure of something is how it looks, how it's built, how it's built different, how it's arranged. That's a good word for it. And what's function? Yeah, how it works. So both of those words that we chose to use, especially built and works, are things we might describe for like how a human being interacts with the world, but the magnets have a structure. They have an internal structure that we'll talk about, and they have a function, which is not only just their job, but it's the way that they work, the way that they, I'm trying to think of a better word, the way that they behave. That makes it sound less like it's being controlled and more like it's how it just is. You know about magnets a little bit, so we're going to talk very briefly about a description of magnets that which you should at least remember from last year, but also probably know from your life. But if we have a magnet, I'm just going to draw a bar magnet here. What do we call the two ends of it? Yeah, well, we might label them north and south, but they are together. They are what? Poles. The magnetic poles are the two kind of nodes of function on a magnet. And if we were to diagram the field that operates around this magnet, the field of force, a force field, right? Because a magnet, I have a little magnet here on the bottom of my fake succulent. A magnet exerts a non-contact force on other objects in its environment, right? What force are we talking about broadly? What fundamental force of the universe are we talking about when we talk about magnets? Almost. That's part of it. No, not gravity. I mean, although gravity does affect this. No, there's a name for the whole force. It's not just magnetism, electromagnetism. Because the electrical force that we talked about in the last video and the magnetic force that we're talking about in this video are one force, electromagnetism. We refer to them differently. We categorize them differently as human beings, but they really are one force. And it's a non-contact force. It exerts a force even if it's not touching an object. So if I have this magnet here and I have it a little ways away from the board and I drop it, well, gravity is acting on it. That's not really what we're talking about today, but gravity does act on it because it has mass. But as it's pulling it down, it also pulls it towards the board. Even though it's not touching the board, as I drop it, well, half the time, as I drop it, a force is exerted on it, and it's pulled towards the board, okay? It's a non-contact force. Because it exerts, as I was saying, a force field around an object. And the field lines kind of go like this. So these are obviously invisible, but they originate at one node and wrap around it to the other. And where do you reckon the magnetic field is the strongest on this magnet? You should have found this from your labs. No, the opposite of that. The ends. On the ends are where the magnetic field, you can tell because of the concentration of field lines. The field lines are denser, they're more concentrated if I draw it like this, or if your book more neatly draws it like this. I think that's going to show up on the camera. I don't actually know. And there's also a picture there of someone has put iron filings relatively evenly spread on a surface, and the magnet holds the iron filings in that place, or it rearranges the iron filings to be kind of in the shape of these field lines, showing how the field lines exist. Because in reality, the field lines of a magnet are invisible, and so someone has used iron filings to demonstrate how the magnetic fields, or how the magnetic fields interact with that iron. Can you think of a way that if we wanted this magnet to, if we wanted to double the strength of maybe the lifting strength of this magnet for objects that are not themselves magnetic, what could we do to this to make it so the field lines were denser in one specific location? Instead of having this magnet as a bar with both nodes, both poles on opposite ends, what could we do to double the strength of the magnetic field on the magnet? Oh, not quite a circle. Try again. Almost. Have you ever seen this kind of magnet? Yeah, we usually call them horseshoe magnets, but it's the same thing as that. It's the same thing as this. It's just bent, and so now the magnetic field lines, some of them will probably still represent, but most of them are just right here between the nodes. There'll be some like that too. And so we get a greater density of magnetic field lines here. And as I say, this would be good for picking up objects that are not themselves magnetic. What we might call ferromagnetic, like the whiteboard or like a nail, where they are affected by a magnetic field. Affected by a magnetic field. But they don't themselves generate a magnetic field. Where we might call these objects that do generate a magnetic field a permanent magnet. Now, does permanent mean that it's actually going to last forever? No, because nothing is permanent. But we call it that because it's continuously, maybe not forever, but continuously generating a magnetic field, as opposed to something like an electromagnet, which exerts a magnetic field only when a current is running through it, or a ferromagnet, which exerts a magnetic field only when it's itself in a magnetic field, or something that's diamagnetic that interacts with a magnetic field in other ways. And a fundamental thing about magnets is that if these two magnets, let me erase the field lines around this one. If I brought these two magnets here that I have on the board close to each other, what would happen? If I have, let's say, if I had both of their north poles touching, let me just draw that up here. If I have this situation, yeah, they would repel. The like poles repel. Like poles repel. What if I switch it? And now I have the north and south pole. Yeah, so opposites, what? Attract. Well, I guess, try like that. There we go. The opposite poles will attract. So that's and one other thing, the reason, I guess I'll use the word reason, the explanation for why magnets exist at all is because, like all matter, magnets are made of what? Okay, like all matter, magnets are made of matter. Yep. Atoms. Yep. Specifically, magnets are usually made out of one of the elements there in the transition metals, largely cobalt or nickel or iron, and they're arranged. I've drawn here some what I hope are clear to you, and you remember from last year or your reading, are called magnetic domains. So these are individual regions of atoms within a magnet, and within them, which the whole magnet is made up of atoms, but each of these magnets is made, or each of these magnetic domains is made up of atoms, and the atoms of iron or nickel are interesting because the way the electrons spin, that's one of the quantum properties of electrons. One of the properties electrons can have is their spin. The way the electrons spin generate a magnetic field. Or, let me phrase it differently. The way the electrons spin can be aligned. So each little iron magnet, each little iron atom has a spin which is oriented in a certain direction. And if those spins are aligned, it will generate a magnetic field. Now, in a normal piece of iron, or in a piece of iron that isn't magnetized, like our nail, there are still magnetic domains in this. It's just that the spins of those iron atoms are more or less random. There's no average or net magnetic field. So in this magnet, I probably should have drawn them a different way, because if it were north and south on the ends, they would be oriented bad. It would be oriented like that, probably. But the point is, they would all be spinning the same way in these fields. And so this little baby area right here gets the net field direction of that way. And maybe this one's that way also. They influence each other. And you know, some of the atoms will spin in slightly different directions, and that's kind of what determines the strength of the magnet. But on average, the electrons spin in a direction that lends this a permanent magnetic field. When this nail gets into a magnetic field, it's ferromagnetic, its atoms will align to be like this one, and that's why it attracts. So they'll align to be the opposite of that way, so that the magnet attracts it. Remember, because opposites attract. What's the biggest magnetic field around? Earth. Earth itself behaves as a magnet with a north and a south pole. In fact, that's why we call the north and south poles of Earth that. Like Santa Claus. He lives there because of the magnets.
No, the Earth is magnet.
That dumpy, ugly man Santa. I'm anti-Santa. I'm more for the South Pole. I'm on South Pole squad. I am a loser. Thank you, Mason. Yeah, I'm sorry. You're right. Actually, the Earth is flat. Let's move on. Now you've completely flummoxed me, and I don't know what I was going to say next. Another thing that this will do is that in the magnetic field, this is all caused by the movement of electrons, right, or the orientation of electrons. But while in a magnetic field, electrons will also flow, and that's a property called electromagnetism. So all of this operates under the electromagnetic force, the fundamental force of the universe called the electromagnetic force. But the idea of electromagnetism as a separate topic is that moving magnets cause a flow of electrons. Do you remember what we call a flow of electrons from the last chapter? What kind of electricity is the flow of electrons? Is it static electricity? It is not. It's the other kind. Current electricity. So moving magnets cause the flow of electrons, which means that they cause current. Likewise, electrical current generates a magnetic field according to something called the right hand rule. Do you all have right hands? Would you show me your right hands, please? You might all have to stop writing, but it has to be your right hand. It doesn't matter if you're right or left-handed. It has to be your right hand. The way that electrical current flows is if your thumb, get out your little right hand, do this with your thumb. Boop, 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 boop. If the current is flowing in the direction of your thumb, a magnetic field will be generated in the direction of your fingers. So if there's a wire, here's the current is flowing this way. If there's a wire and the current's flowing this way, maybe the battery's over here and the light bulb's here, I don't know, a magnetic field will be generated coming out and around the board like that. That's called the right-hand rule. So a magnetic field will generate around that. I'm trying to think of a good example. Usually nowadays wires are well enough insulated and carry low enough current that it's not really a problem. But sometimes I have like a 10-foot HDMI cord going to the television set, and sometimes it was the case last year that if someone would move nearby the HDMI cord with something magnetic, or if they would even just, I don't know, if they would just look at it. But magnetic fields in the room would cause problems because it would disrupt this current due to a magnetic field being in its presence. An example of that, an example of the uses of that is your book talks about speakers and it talks about electromagnets in general, but the two most useful one, you should probably be aware that's how speakers work. I don't know if you've ever thought about how do speakers work, just magic, right? Like I put them in my ears and then, but what's actually happening inside of a speaker, here's your AirPod, other brands are available. Inside of it is a little, what's called a diaphragm with a magnet on one end. There's a magnet here, and that magnet is attached to a wire in the battery. Here's the little battery down here. And there's a gap between these magnets, and as current is generated, it will suck this diaphragm back or push it forward, because this magnet could either attract or repel the other magnet. And it does this in such a way, there's a little computer in here too, and some like Bluetooth transceiver, and the Bluetooth transceiver goes to your phone. This is your phone.
Why is it smaller than the
You got a really tiny little phone. It's a fruit snack. But your phone tells it to play Skippity Toilet, and what happens is that the computer in here attracts or repels this diaphragm using a magnet, and then because you remember from last year that sound is caused by vibrations, the vibrations of that diaphragm, it does this in such a way that the magnet's attraction and repulsion generates movement in the air, which your ear perceives as sound. So that's how speakers work. It's the opposite with microphones, as with many things in magnets. If we this is a microphone, and if we take this little microphone, which looks like that, it's the opposite. So it's the same, a similar setup. It's got all the stuff in there too. But what it's doing is recording. It's as the diaphragm moves due to the sound of my voice, it is touching the magnet, and the computer within it, or transmitting back to my computer, records the modulation in that diaphragm, and that's how sound is recorded in a microphone. This microphone, it's all right. I don't want to curse it in the middle of the video because then it'll just turn off, and I do believe in jinxes like that. And so it's okay. It's not great. I mean, it's not the world's best mic, but it's nice that it sits on my lapel here, and I can. Actually, I think this one came from TikTok Shop. It was like $6 for two of them, which might explain the quality of the sound. But it's nice because it's right here, and it can mostly hear me, and when you guys are jabbering, it doesn't pick up mostly what you're saying. So that's how speakers and microphones work. But another, and I wasn't even really going to talk about this, but another really useful thing about electromagnets, or the property of electromagnetism, that moving magnets cause the flow of electrons and electrical current generates a magnetic field, is the idea of a generator and a motor. And like the speaker and the microphone, these are they're not opposites, but they're like reverse. And I'm going to show you an example. So here I have a hand crank generator. And as with all generators, what happens is if I move it, this little gray thing in here has a magnet. And as that magnet moves, it will generate an electrical field. Okay? And that electrical field will generate an electrical current. It will go in these wires, and it'll go to my load. And the load here is this little LED light. And so as I crank this, I'm going to be generating electricity by moving a magnet. Generators use, let me do this in a different color. I'm kind of getting a little bit chaotic, so I'm going to do this in a different color. Generators use a moving magnet to generate electricity, electrical current. I'm going to link that to, I did it wrong. I'm going to link that to my definition of electromagnet, where moving magnets cause the flow of electrons. Okay? So as I move this magnet within this gray cylinder in here, it will generate an electrical field. Whoa! Look at that! Oh, do you see it? Put it on my hat. Oh. Now I'm just being ridiculous. This is disgusting. There we go. In the armpit. Blue dot. Is it working? Oh, no, now you actually have caused it to break by telling me to do that. It's my fault, but you told me to do it. LEDs can only take a certain voltage, and if you get too high a voltage, it will break them. So now And also, you might notice just by the sound, I have this really close to the mic, the sound is higher pitched because this has no resistance now. I mean, it's like pedaling a bike when the chain is off. It's like woo, woo, woo. Whereas before it was kind of, I mean, it wasn't hard to crank even for me, but it was like that. And now that the LED is dead, the circuit has been shorted out. Thanks a lot. This has to go in the trash. Now it's really easy. There's less resistance. Remember Ohm's law? So I'm generating with the much less resistance. I don't have to have as much current. But check this out. Check this next thing. I'm going to do this one in green. In a motor, a electrical current causes a magnet to what? Guess. To move. It's the reverse. So I'm going to put this electrical source, this battery, on the generator now. And check out what's going to happen. No. What do you hypothesize is going to happen? Ta-da! Oh, that probably hurt. Ow, it does hurt. But check out, guess what we could do? We could put a wheel on this, and we got a little car, right? We could put a propeller on it, and now we got a little boat. Because sometimes it's nice to have a battery do your work for you. That's called a motor. And other times it's nice to something that's already moving, just stick a magnet in there and you can get electricity. Give me some examples of that. What are some examples of generators? Oh, I don't want to talk about an alternator right now. I want to talk about generators. A wind turbine, yeah. A wind turbine is a very simple one. The wind's already moving, so let's stick a generator there and make it so it can give electricity to people's houses. Hydroelectric is another one. The way that all the other power plants work, except for steam, is they have a generator, a turbine, something that's going to spin, and a fluid moves over them. Even in coal and oil and nuclear, thing get hot, thing boil water, hot thing boil water, the steam gets pushed in through a turbine and that generates electricity in every single one of those cases. So coal, oil, natural gas, nuclear, all of those are just thing get hot, water makes steam, steam turn turbine. That's how those things generate electricity. And then in hydroelectric and wind, it's because that fluid is already moving. In solar, it's completely different. That's a process called photovoltaic, where some chemical compounds, when light is shown on them, generate their electrical current, and that's a whole different thing. But that's how power is. We've just discussed all of the ways that power is generated in the world for human consumption. And we talked about why. I mean, you already know why motors are useful. It's nice to have things move. Wheels, propellers. Do you have questions about magnets? I feel like I might have more questions about magnets now than when we started, but I'm glad that you don't have any questions. I'm glad that you have complete understanding of the world of magnets. Bye.